will be Google Classroom, the first year, first semester, and you will find all the materials which I will post in this virtual classroom. So you are all enrolled here, right? Now let us come to your concern, the course material page from my desk. So you will find that there are different chapters, and under different chapters there are different topics. So when you will click on a particular topic, it will open from the Google Classroom. So since you have the access to the Google Classroom, you can easily visualize the course material. Now let us come directly to the today's course. Today, my course is basically based on the formation of the molecular orbital from the atomic orbitals. Now, the atomic orbitals, if they join together, they produce molecular orbitals. So, if two atomic orbitals they are joined together, they will give you two molecular orbitals. One will be the higher energy, and another will be the lower energy. Now the question is that when the atomic orbitals they combine with each other, in how many stereochemical fashions they can combine? So stereochemical fashion is the way of approach during the formation of that orbital. So the approach of the two orbitals is of two types. One is head-on approach and another is the lateral approach. The head-on approach will produce sigma orbital. On the other hand, the lateral approach like this will produce the pi orbital. Generally, from class 12 level, we know the head-on overlap basically makes sigma bond, which is more stabilized, and the reason we generally talk about is the more overlapping region. In the case of lateral overlap, since the overlapping region is less, we always argue that pi orbital is of higher energy, because the more overlap, more stable. Less overlap, less stable. But that is a very preliminary concept. Let us come to the energy level diagram for the formation of the molecular orbitals. Now you see the left hand side diagram is corresponding to the formation of the sigma bond, and the right hand side molecular orbital diagram is basically for the pi orbital formation. And in both cases, we have taken two atomic orbitals at a time. So in the left hand side, when the two orbitals are combining with each other in the head-on fashion, they are making two sigma orbitals. One is of bonding nature, another is of anti-bonding nature. The bonding orbital is of lower energy, whereas the anti-bonding orbital is of higher energy. So, what is the reason that bonding orbital will be lower and the anti-bonding orbital will be higher? Because the bonding orbital has a dense electron cloud in between the two nuclei, whereas in the case of the anti-bonding orbital, the two nuclei have a nodal plane in between them. That means there is no electron cloud in between the two nuclei. So obviously that will be higher energy. Okay? So higher the energy of the orbital, higher will be the number of nodes. Right? Another very interesting feature of this diagram, that there is an energy difference between the very center, which is the middle line of the diagram, and the lowest bonding molecular orbital. Right? So that energy is called the stabilization energy. What is called? It is called stabilization energy. Fine? And similarly, we will take stabilization energy for the pi orbital. Now if you compare these two energy diagrams side by side, it is clearly visible sigma 1 formation is higher than that for the pi orbital formation. Or in other words, you can say that sigma orbital is more sterilized than pi orbital. Right? Is it clear? Okay. Now let us come. This is a pictorial presentation how the sigma orbital and the pi orbital are looking like. Clearly it is indicating that sigma orbital is by Hadron overlap, that is along the molecular axis, and the pi orbital is perpendicular to the molecular axis. So one set of electron is above the plate, another is below the plate. Now, if we just stack the energy levels of the two set of orbitals are making sigma as well as pi, because in the previous diagram I have shown the sigma diagram and the pi diagram separately, right? But in real scenario, how they are stacking after each other. Stacking means you have a proportional geometry, right? How they are stacking after each other, because they are the diagram is separate, but in reality they are two diagrams you have overlap. And there you see the lowest one, which is occupied by the 2 electrons, and then another orbital which is designated as HOMO, which is also occupied by the 2 electrons. Now the lowest one is the sigma and the upper one is the and the LUMO is the pi strand orbital, and the highest energy containing molecular orbital is also sigma star. Allylic orbital, a very interesting feature. Now, when we will consider the energy level of the frontier molecular orbitals, in case of alloy, we do not consider the sigma. Generally, in case of alloy system or quantinucleotide, that is in case of long conjugated system, we always consider the frontier molecular orbitals as the set of the only the pi orbitals, not the sigma orbitals, right? They are only designated as the electron. তাই electron হিসেবে তাদের নামকরণ করা হয়, right? Now, if you look very meticulously at the allylic carbon, you will see that the 3 carbon atoms are in the same plane. Out of the 3 carbon atoms, the 2 carbon atoms are involved in the formation of the pi bond, and the pi molecular orbital is HOMO from the previous diagram. So, one HOMO is just adjacent to the vacant pi orbital, and the HOMO is high in energy, so it is very reactive. So it conjugates or disperses this electron cloud with this adjacent vacant p orbital on the carbon atom. That means it is called the resonance through conjugation, right? So that's why I have drawn the dispersed electron cloud over the 3 p orbitals in the allylic system. That means resonance frequency. Now let us consider the energy frontier molecular orbital energy diagram of the allylic system. Frontier orbital energy diagram. Frontier molecular orbital energy diagram of the allylic system. Since I have told that we are considering the FMO, frontier molecular orbitals of the allylic system, only the pi orbitals, so we are not considering any sigma, right? So here are the 3 p orbitals, so you are getting 3 pi orbitals. So p orbital are always giving pi orbital to lateral orbital. So 3 atomic orbitals, you are getting 3 molecular orbitals. Since it is parallel, so it's pi. So one is pi 1, one is pi 2, one is pi 3. The lowest one is having no modal length, so it is the highest stabilized molecular orbital among the pi set of orbitals. The second pi 2, which is basically the HOMO. The first one, pi 1, is basically this HOMO. The pi system has altogether the 2 pi electrons and the magnetic orbital has 1 electron. So altogether there are 2 electrons. The pi electrons. So the pi 1 is the HOMO, and the pi 2 is the LUMO, and pi 3 is the highest unoccupied molecular orbital, and the 2 nodes. Right? So if you increase the number of if you increase the energy of the orbital, the number of nodes will increase. And the number of nodes is basically the level of that energy level of that molecular orbital minus 1. So level is 3 minus 1, 2 nodes. Level is 2 minus 1. Number of nodes is 1. Level 1 minus 1 is 0. Right? Now this is allied cation, allied anion, allied radical. So left one is allied cation, middle one is allied radical, and the right one is the allied anion. And if you just compare, you will see the number of orbitals, that's the number of electrons in the pi 2 is gradually increasing on going from pi allied cation to allied anion. Right? And mind you, here pi 1, pi 2 and pi 3, among these three, pi 1 is the bonding, pi 3 is the anti-bonding. In this case, interestingly, pi 2 is called non-bonding. Right? The middle one is always called the non-bonding. With respect to non-bonding, the same set of orbitals which will be lower, that same set number of orbitals will be on the upper side. And non-bonding orbitals will be in the middle. তাহলে non-bonding orbital এ যদি উপরে দুটো orbital থাকে তাহলে নিচে দুটো orbital, উপরে যদি তিনটে orbital থাকে তাহলে নিচে দুটো। So non-bonding orbital is basically here bisecting the energy level